Today is April 12. We're back from spring break, and I'm just reviewing what we did two weeks ago. 3 weeks ago, right? 2 weeks and a half ago. 2 weeks and a half ago. So we are finishing chapter 28, and we are closing chapter 28 by studying the circuit of a capacitor and resistor. Okay, so we go ahead, connect a power supply to a resistor and a capacitor. We put a switch there in the circuit. Right now the switch is open. Because the switch is open, no electricity, no current flows through the circuit. When we close the circuit, we have this current flowing immediately through the circuit. The capacitor is initially uncharged. Okay, the capacitor initially has no charge. That's why we have a number 0 here. This number 0 states that the capacitor has no charge whatsoever. And this is a very important circuit. Okay? And whatever you're going to derive here is exactly what happens in real life. Okay, as the current flows through the circuit, the direction of the current, remember, is the direction of motion of the positive electric charges. Okay, so here you have positive electric charges moving in this direction from the circuit, and then what's going to happen? Those positive charges are going to accumulate on this side of the plate of the capacitor. Remember that we have a gap between those two plates, and electric charges cannot jump the gap from one plate to another. So they're going to stop right in here. Okay? In the process, the positive charges are going to attract the negative charges on the other side of the capacitor. Okay? And that's what you're going to do. That's what's going to happen. You start with this larger current, but as the capacitor becomes charged, it's going to try to pump a current on the opposite direction, which is going to cancel a little bit of this current. Okay? So little by little, the capacitor is going to become more and more charged, and the current is going to decrease. That's how we treat that system in a qualitative fashion. Okay? Eventually, there is so much charge in the capacitor that the capacitor is going to be able to cancel out the current flowing, the current that the battery is pumping into the system. It is at this point that the voltage in the capacitor, the potential difference between the two plates in the capacitor, is equal to the potential difference on the battery. Okay? So if the potential difference in the capacitor is V, the potential difference in the resistor is going to be 0 because there is no charge flowing through the resistor. Remember, V of the resistor is Ri. If I is equal to 0, the potential difference across the resistor is going to be 0 as well. And we derive that. How do we derive that? Okay, we use the Kirchhoff loop law. There you go. Negative charge here. Here is supposed to be negative as well. Let's make sure we save it. Okay. Kirchhoff loop's law. We did that. Go back to my notes. Right? Kirchhoff's loop law. We started the battery, goes from the negative, or power supply, goes from the negative to the positive, is a potential difference V. We goes through the resistor, that we have a loss of potential difference, which is IR. Okay? So minus IR. Then we cross the capacitor from the positive to the negative. We lose potential difference. Is going to be minus VC. Minus VC, it's going to be Q over C. Minus Q over C. And that's what you're getting. V minus IR minus Q over C equal to 0. That's how we get this equation. We get this equation using Loop's law, the Kirchhoff loop law. Let me write that down here for you. We solve this problem by using Kirchhoff's loop law. Kirchhoff's loop law. Don't forget that the current is dq dt. The current is positive. The capacitor is charging. Capacitor is increasing on the amount of charge. Okay, dq is positive. Consequently, I is going to be positive as well. So we go ahead and, let me see how I did that. Okay, we keep this value here in your head, right? And then what we're going to do next, we are going to differentiate both sides of this equation with respect to time. That's what I did here. dv dt, dir dt, dqc dt. Okay, the v is constant. Consequently, we can, when you differentiate with respect to time, it becomes 0. The resistance doesn't change in time, but the current may change because the capacitor is acting against the power supply. So you get R di dt, dq dt. C is a constant, depends only on the geometrical properties of the capacitor. We are not changing the geometrical properties of the capacitor, so we can take it out, the 1 over C. And we end up with this term here, dq dt, that is I. And now we have a differential equation that we can solve. That's the type of differential equation that you folks have seen in Calculus 1. Okay? So go ahead, separate. We gotta go separate the two elements of the differential equation. Then you have to separate the variables. Okay, so in order to separate the variables, I have to have I, the dependent variable, on one side, t, the independent variable, on the other side. And that's what I have here. dt goes to the right, I go to the left, and that's the simple differential equation that we can solve. All you have to do is to apply the integral to both sides. Okay, apply the limits to the integral from I naught to I, and the for t goes from 0 to t. This integral is easy, right? It's just going to be t divided by CR with a negative sign. The integral of the inverse of the current is going to be log of I. Apply the limits as well. Here you go. Invert the left side of the equation, and we get an exponential decaying exponential. I divided by I naught is exponential, okay, to whatever. This I naught. The question is, that one, okay, that we didn't finish the problem. We didn't finish the problem. The question is how to obtain the value I naught, the initial current. So we solved most of the problem, and now we have to know what is the value of I naught. Okay, that's, we did most of the grunt work, and now we're gonna do something else that's not easy to find because it requires some thought, some thinking in the process. Okay, so here we go. We determine I naught. The way we do is the following: we determine I naught by analyzing uh, how do I do that here? Analyze. Here you go. This circuit at t equal to 0. That's how we do it. Okay. Okay. So what's gonna be the piece of information that's gonna provide you the value of I naught. Okay, so let's take a look. Look at the circuit at t equal to 0. What we have? The voltage through the battery is V. That stays, the voltage through the power supply is V. Value that remains constant throughout the experiment. Okay. Here we go. Have the following one: the voltage through the power supply is V and remains the value throughout the experiment, like that. Here we go. Next, the voltage through the resistance obeys Ohm's law. And when I write that down, I have V lowercase r, right? Subscript is going to be Ri. Subscript. Let's see, subscript. Like that. Okay, well, this Ri is actually Ri naught, right? Let me see if I can put it I naught there. Yeah, here you go. I have I naught here. Go. Like that. And then finally, don't forget, I'm talking about the voltage at time t equal to 0. And then we have to ask ourselves, what is the voltage across the last element, which is the capacitor, you know? Remember, what's the voltage across the capacitor? Okay? Remember that initially the capacitor is uncharged. What does it mean the capacitor is uncharged? You know, Q equal to 0. That's what it means, Because this implies that that the potential difference across the capacitor plates is 0. Make sense? The two plates, right? Let's go back to the drawing. Here you go. At time t equal to 0, there is no accumulation of charges on this plate here. If there is no accumulation of charges on this plate here, there is no electric potential difference between those two plates. So at time t equal to 0, the V, the potential difference across the capacitor plate, is going to be 0. Okay? And now we start to have an idea, an inkling of what's the value of I naught. How? Go back to the Kirchhoff's loop law, okay, that we had before. That's the generic Kirchhoff loop law. Apply. Now, here you go. What's going on here? Nope, don't save it. Okay. Go back to the generic Kirchhoff loop law, okay, and apply the values of v at t equal to 0. Okay, so v remains v because the potential through the battery doesn't change. I flowing through the circuit now is going to be I naught because it's the current at time t equal to 0. And V of the capacitor is 0. I'm going to write like that. We know V, we know R. We do not know I naught. We can solve for I naught. We can solve that for I naught. And now everything that we're finding here is through Kirchhoff loop law. That's how we find the value of the initial current I naught. Okay, we solved that for I naught. Let's see. V divided by R. Okay. We can now finish our problem. Okay, the current. The current behaves like that. Okay. What you have here is the unit for current, the initial current. So that's how we finish this problem. You can plot it. Let's see if I have a plot that for you. It's what that thing tells us. It tells us that the current decreases exponentially. Okay. Go. Okay, negative. Let me see if I have a. I don't have. Yeah, I have to do that. Let's see if I have it somewhere. Oh yeah, that's how the current decreases. It decreases exponentially. I need to place this guy elsewhere. Okay, so here go. Here. Yeah, I don't need that. Yeah, this one can go. Okay, that's how the current decreases. It starts at a very high current. As time goes by, it decreases until it goes to 0. That's exactly what they. And like I said, something like that is real life. This is exactly what happens in the lab. Okay, at times, a very large instance of time, this exponential becomes 0, approaches 0. And then we can go ahead and find other things. We can find the charge in the capacitor. How do we find the charge in the capacitor? That's straightforward. How do we find the way that the charge varies in the capacitor? Okay, current is going to be dq dt, right? Here you go. We separate the variables. Dt goes to the other side. Dq dt. Like that. We integrate on both sides. Okay, I'm running out of power now. Wow, wow, wow. That's not good. Anybody has a power supply for their laptop that I can borrow from you folks? No? No? Let me see if something else is going. No, but that's not gonna help. Well, let's keep on going, until I run out of power, and then I do something else. Uh, let's see how much power I still have. I have 20% left. Okay. Once I run out of power, we have to. I won't be able to record this class. Okay. So here you go. Apply the integration to both sides. Don't forget initial charge. Right. I'm going to go. Come on, man. T from 0 to T. Initial charge in the capacitor is 0 because the capacitor started uncharged, and this integral becomes what? Becomes, oh, let's see, we gotta put something else here. Right? We put it CR, oops, CR, and we still have a negative here in front. And don't forget, we have to apply the limits. Okay, from 0 to T. We apply, let's see, yep, I'm gonna take this CR out to put it here in the factorize. And what else? Okay, minus becomes plus. Apply t equal to 0. Exponential to 0 is 1. One more step. I don't need the limits anymore because I already applied the limits. The R cancel out with the R. We end up with VC, which, by the way, VC has units of electric charge, and electric charges, you know, let me see here. I'm going to readjust. Okay, it's like that. Whenever t equal to 0, this term here is 1. 1 minus 1 is 0. It matches what we have. Whenever the t is very large, this term reduces to 0, and we get a charge is equal to CV. CV has units of charge due to the definition of capacitance. Okay? So, what else can we do? In addition to find the charge in the capacitor, we can also find, here you go, I should have done that before because it was easier. We can also find the voltage across the resistor. And that's easy, that's straightforward. The voltage across the resistor is what? Is Ohm's law. We can use Ohm's law. Voltage across the resistor, here you go, is Ri. Okay? So that's easy, right? Here you go. So the voltage across the resistor behaves in the same way that the current across the resistor. It's just the electric charge that behaves differently. Why is that? Because we start with a charge 0. Okay, let's save that. And what time is that? It's 5:30. You know what? I want to save electricity here of my laptop. I'm going to start charging it, okay? And let me pause before